Okay, great. So, yeah, we're going to talk about quantum software. You've heard a lot about hardware developments, and I think rightly so. 95% of all investments in quantum are going into building better qubits. Of course, there's no software without hardware, so that makes a lot of sense. But what we know from classical computing is that 70% of all the value is created by the software stack. And so now's a really interesting time to talk about, well, what does that mean? What are the opportunities, and what needs to happen to encourage that ecosystem? Yeah. So thank you for joining me.
Yeah, absolutely, Steve. Kick it off. I fully agree the role of the software, the importance of it. But let's dive in exactly saying how. So everybody says software is important, but let's discuss about the how. And I think it's very important to say how the things are changing. We're all getting super excited about fault tolerance. All those building blocks start emerging. We're seeing logical qubit, mid-circuit measurement, all those new pieces of puzzles are coming. And I think it's so crucial right now. We learn what we saw in the area of the NISQ, that how we had this smart abstraction that allow the software people, algorithm development, to have the right level of abstraction of understanding, okay, what's the element of our hardware? What is connectivity? What is the native gate? And so I can do the hacking well, and yet not to get too much to the details. And to me, I think is the call for action, the same thing regarding fault tolerance, that these new pieces of the puzzles are coming, these new Lego pieces. And it's so important to have a software, a sandbox that now that as the designer of an algorithm and application, I can start again hacking, but with these new pieces of puzzle. So it's super exciting to really create that available. So hand over to you. How do you do that? How Riverlane is actually doing that, such a software to make us to get the best performance of our algorithms?
Yeah, it's kind of like you could say to somebody, hey, I've got 3 logical qubits, and you can do, a logical control knot between them. Like, that's going to be a pretty boring platform. And that's probably where we're at for the next few years, at least. So I totally agree that would be too high an abstraction, right? And really what you want to do is expose the interesting part of the puzzle right now, which is how to do error correction well. There are so many ideas coming out of research, coming out of companies and in the community around how best to implement quantum error correction. There are whole different types of codes. There are different ways to do logic. We know from the NISQ era that if you can tightly couple how you implement the next bit of the stack with the one below it, you can do a much better job. So yeah, I definitely agree that for the next 5 years or so, like the right abstraction is going to be exposing that error correction layer, and that's where this next generation of software developers plays and really learns how to do that well.
Yeah. And I would say that I go one step further. So we're talking about, indeed, everybody knows you need to have a better quality of qubit in order to design better algorithms. So this software that you were mentioning is going to completely change the way we get the best performance of our algorithm for the quantum utility application. But something even more is that it's not just about the algorithm performance, but actually the feedback loop that we need to give to the hardware. So the analogy that I want to go quickly now, like error correcting code, surface code was designed ages before qubit even existed, no? And that's very much influenced the design of superconducting qubit. At the same time, fast forward, LDPC code comes, and now suddenly we want different type of error correcting code. And now we need to look at the different architect. And this is not the way it can work out. If you're seriously trying to scale up, we cannot build a super expensive machine, quantum computer is very expensive, and now let's change the design. Let's change the tire of the car. It doesn't work like that. So I think the importance of software is not just to get a bunch of application and use case and sell it to the investors, but in fact, crucially, at this very moment, influence the way that the hardware is designed. So I think this is now the moment everybody talk about co-design. But if we don't get it right, we're not going to be able to scale it up, because the software can tell us, how do I test? How do I know what do I need to have it, so that can be influenced on the hardware design as well?
Yeah. And I think that feedback cycle is also important for developing error correction itself. So one example that Riverlane have found over the last year has been that we can adapt to dominant sources of errors in different qubit modalities. So, for example, in superconducting systems, leakage is the dominant source of error, where instead of being a 0 or 1, you leak into this 2 state. And by adapting to that, we can make error correction more efficient and reduce the overall footprint of the quantum computer by factors of around 5x. So a 5 times smaller quantum computer with the same logical capability. And so that feedback cycle within error correction is definitely there. I also see it actually in the algorithm layer. So this kind of first generation of error-corrected quantum computers, this sort of megaquop era, is still going to be pretty tight. Like 1 million error-free operations, it sounds like a lot. It's like way more than we have today. But we're still going to want to squeeze every ounce of performance out of that system. And so I think that feedback cycle between the algorithm and the implementation of error correction, I also think that's going to be really critical in the next generation.
So we agree. We cannot disagree. Yeah. But I'm going to ask a question that, so as an academic at the NQCC, at the Quantum Software Lab, getting all this knowledge, all this optimization, all this hacking, all this architecture is something that we love and we do and we share. But now as a commercial software company, how could you still get value, commercial value, while enabling? I mean, you're a partner in many testbed projects in the QBI. So what's the trick? How do you do the balance?
Yeah, I think it's important to understand as a company where are you building value and where are you creating a greater value by engaging in the ecosystem. So for Riverlane, we're building essentially the hardware you need to enable error correction. So the classical hardware. So there are no qubits in our stack, and that's a classical semiconductor problem. And I often say that Riverlane's really a classical semiconductor company. We're designing chips that enable error correction. So that's the kind of core of the business. And then if we can lift up the whole ecosystem, that just creates a bigger market, creates a bigger pie. So that's really a win-win. And I certainly believe that we won't have all of the best ideas as a company. Going out and I think in collaborating with academia, with the rest of the broader ecosystem is very positive for both the company and I think more generally.
Fully agree. I mean, I'm pretty sure at some point, if we let audience also ask questions, they will bring the case of skills, because we would like to build this software. We would like to create that influence, but everybody was talking about the workforce, So that's exactly that collaboration that you're mentioning, giving access to the hacker and creating those hackers through, all level, PhD, expert, software developer, to trying to ensure we are ready. Forever, we need to be ahead of the hardware to go through. So I'm super looking forward to that kind of collaboration as well, to accelerate once we have this fantastic toolkit to play around with.
Yeah, there are probably 300 people in the world who understand quantum error correction right now. So that's a pretty small number, right? And so I think of this like, if you were in AI 5 years ago, like what do you wish you'd done then, right? Because you could have the opportunity to do that today in quantum. And so, if you're at the beginning of your career, like one of the great things to do would be to learn quantum error correction, right? You could be one of a very small number of people in the world who really understand a critical bit of quantum computing. And I see this as kind of the people who will be like the kernel developers in quantum software. So the kind of core to any software stack will be how you implement quantum error correction, and then you'll build applications on top of your logical qubits. So it's really a brilliant time, I think, to come into the quantum space. But we as a field then need to enable that and to provide the tools to make that easy to learn.
And of course, we need to test all those tools. So we can talk about verification, perhaps, my favorite topic, because, building the tools and looking at the verification, benchmarking, certification, whatever you want to name it, is going to be very crucial part of this, acceleration, because we want to have a trusted way of accelerating. We just don't want, we heard about the panel before, which were saying it, avoiding hype, but also certifiable. So I think I like to just, before we're going to the question that is coming, to talk about this issue of, oftenly maybe people are missing about, how complicated it is to look at this full idea of the verification. Because of course we're reaching with the quantum to the area that they are no longer classically simulatable. So you cannot just cut and paste what you were doing in order to do the testing and checking that existed in the software stack. So I think we are seeing that whether you want to look at your algorithm performance benchmark, whether you want to see that your device is working the way it is, even if it's fault tolerant and error corrected, if you want to see all the component there, this is a very sophisticated, what I call verification stack that need to go again into the software stack. The good news is we are doing it at NQCC, and Michael will tell you later on all about this, how is the core to element of our testbed. But I think everybody, QBI, also collaborating, many of the partners are seeing this benchmarking verification, whether it's at the software or hardware, is also a very important element. Again, another software enabler.
Yeah, and it's maybe a bit surprising in a way. I mean, what does it mean to verify a quantum computer? Like it's exploring these many universes, but like, how do you test that? How do you think about verification? I mean, you talked about benchmarking, but what does it mean in practice? Like I show up with a quantum computer and then what? Or is it a deeper collaboration?
Bring it to the test bed. I'll answer you. I can spend the next hours to discuss that, but I think it's a very important, the question that say, even people understanding that that's the question, I think is a good beginning. And then the solution will come. But it's just now that people start understanding, now we need to, the metric that we have is no longer enough. We heard from a few panelists before. So we are in that area that we are scaling up, and hence our verification needs to scale up. Should we take the question?
Yeah, so we have a question. Yeah.
So what are the challenges facing collaboration in the ecosystem?
Yeah, maybe there's two I could think of top of mind. So one is where different people in the ecosystem expose different parts of the stack. So if a company comes along with a black box solution that doesn't enable you to play around with the part that you're interested in, then you can't collaborate, right? So you might see this, for example, there's lots of really interesting work around control systems. People have lots of really interesting ideas about effectively applying optimization type techniques within control pulse generations. Some companies expose that and others that didn't. And that's kind of been that's often a moving target. You know, I think the ecosystem responds. So I think the kind of openness of various, to maybe come back to the earlier question, like
exactly.
Potentially closed company solutions. I think that's one challenge. Yeah, and I think the other is just the broad base of skills that are needed to go from, I'm going to build some qubits and then I'm going to solve a problem for a pharmaceutical company. I mean, that's such a vast breadth. And I think that means that there are lots of different disciplines working together, and that often creates an artificial barrier, really, of language. I mean, just a simple example, like a chemist would talk about low energies, and a mathematician would say like small eigenvalues. Right? They're saying the same thing, but they're using different words because they come from different disciplines. And I think that kind of nature of quantum computing is a sort of inherent challenge. It just needs people to be mindful of communicating well.
Exactly. I mean, I just want to second what you're saying. And again, bringing back to the topic of software, it's easier to collaborate on software. You know, it's like essentially software, this enabler, as you already mentioned, that the goal of the entire software, whether verification, algorithm design, etc., is in order to accelerate, because as you say, then there will be enough advantage for the entire ecosystem. So I think it's very important to push for this open source software or like this sort of collaboration, because software on its own cannot do anything if you don't know exactly what's the bits and pieces on the hardware side. And I know that there is so many different models to go forward, but I would definitely say unless we are all coming together, we're never going to make it to the area that is beneficial for everybody. So another question is coming. Can Copilot understand quantum secret? Well, maybe they should. They just need to get the crash course. But the point of software, a smart abstraction that I want to say is exactly like that we need to understand now how much of the details we need to understand to do the designing. But again, also abstracting away from where we want to, where it's not necessary. And that's that's the job that I guess we're going to see more and more. Can we call it the third quantum revolution, which is all about the software and an application to make sure that we don't build infrastructure that's sitting there. There is no use for it. And I think that's where we're going. Want to get the last one? Wondering whether verification will use AI. Of course, everything needs to use AI on the record. But it's a, do you want to answer that?
Yeah, I think it's a good example where like there are great ideas, and if the tools are available, then people can try them. Because I don't know the answer whether it's a good idea or not. Certainly, there are lots of classical verification techniques that will be very useful in quantum computing as well.
Yeah. Fully. I mean, just bring an example, it's already many companies, including qBlocks, is already using clever techniques from AI to help with calibration. So we already know in order to get the best calibration, we can use the AI. But it's the same thing in verification, because after all, you're running a lot of data and you want the most optimized way to figure out where is my noise, what thing goes wrong or what's not going wrong. So in simple tool, AI is essentially one part of our verification stack. But again, I want to emphasize, is nothing out there that you can just cut and paste in order to solve the verification question, but all the tools can be used for the sake of certifying we are where we are and where we are going to go.
So we are out of time. I thought maybe just to end, I think in 2018, I would say there was the kickoff of the NISQ era. And quantum computers were suddenly made available, and the tools were available to people to experiment. And it caused this explosion in new developers coming in and people getting excited about quantum computing. I think 2025 is going to be the year that the error correction era kicks off. And it's exactly the same opportunity to create this ecosystem that learns about quantum error correction and become the first generation of quantum software developers. So I'm really excited.
Absolutely. It's the year of the software. So
thank you for listening.
Thank you very much.